about symmetry. This is still chapter 5, section 6. Symmetry is important for integrals. The use is, the benefit is, it makes the computation easier. So what type of symmetric functions do we know? For example, even functions, odd functions, they are symmetric. Even functions are symmetric with respect to the y-axis, and odd functions are symmetric with respect to the origin, right? So if that's the case, let's in this part, actually the functions that we are going to be discussing is going to be a function that's continuous on the closed and bounded interval, but this interval is symmetric as well. Okay, so if a function is an even function, okay, let's remember even function is the same as f of negative x is equal to f of x. This is the graphically, actually, for example, y is equal to x squared is an even function. It's symmetric with respect to the y-axis. And if you have an even function, and if you want to integrate from negative a to a, then the result is actually, in short, you can integrate just half of the interval 0 to a f of x dx, and you're going to multiply by 2. The reason is, you can consider roughly, since we are dealing with an even function is symmetric with respect to the y-axis, and the area underneath the curve to the right and to the left of 0 is going to be the same. And you consider yourself finding the area underneath the curve. Since the areas are the same, you just calculate the area from 0 to a and then multiply by 2. Okay, this is a shortcut. If f is odd, then f of negative x is equal to negative f of x. That's the definition, right? And it is the same. It means then f is symmetric with respect to the origin. Then when we have that, negative a to a f of x dx is going to be 0. Why is that? Let's give an example to an odd function. Y is equal to x cubed is an odd function. If you consider, it is like a s, but in the opposite direction. And underneath the curve, since it's symmetric with respect to the origin, the area under the curve to the right is going to be above the x-axis. The area underneath the curve to the left is going to be below the x-axis, but they have the same equal area, so they cancel each other, right? Okay. So it makes it easier. Here are some examples. Yeah, here's a very famous y is equal to x squared function. We know that this is even, and negative 3 to 3, and underneath the curve to the right of 0 and to the left of 0 are equal. So negative 3 to 3 x squared dx is going to be the same as 2 times 0 to 3 x squared dx. So it's 18. It's easier. Here's y equals to x cubed. As you see, it is symmetric with respect to the origin, and to the right of 0 the area is above the x-axis, to the left of 0 the area is below the x-axis, and they are of equal size. And the integral from negative 4 to 4, it's going to be a1 minus a1, which is 0. This is reasonable. F of x is equal to x to the 6 plus 1. It says find the area, find the integral. And then second question is tangent x over 1 plus x squared plus x to the 4. Find this integral, negative 1 to 1, 10x over 1 plus x squared plus x to the 4 dx. Be careful that the interval is symmetric, negative 2 to 2, negative 1 to 1. So immediately you just say, why don't I check the evenness, oddness of the function? and then the first function f of x equals to 6 plus 1 is even. So we are going to be calculating from 0 to 2 and multiplying by 2. That's it. So here's the solution you would see. Okay, just calculate from 0 to 2 and multiply by 2. This is easier. And how about f of x in the second example? Let's look at f of x and f of negative x. F of negative x, since tangent x is odd function, negative tangent x, right? Tangent negative x is negative tangent x. And nothing changes in the denominator because squared and fourth power. You will see that f of negative x is negative f of x. So this is going to tell us that f is an odd function. That means it's symmetric with respect to the origin. So the area underneath the curve to the right is above the x-axis, and the area underneath the curve to the left of 0 is below the x-axis. So, and they're of equal area. Therefore, negative 1 to 1, the integral is going to be 0. Next section is areas between curves. Before we get to that, let's go back to the slides. Okay, if you see this slide, this is in A, it is telling you that f is an even function, right? It is symmetric with respect to the y-axis. It is symmetric, so if they are asking you to find the integral negative a to a, just calculate integral from 0 to a, multiply by 2, because they have the same area, right? To the right of 0 and left of 0. Okay, on the other hand, in the example in B, this is symmetric with respect to the origin. Why? It's obvious, right? It's symmetric with respect to the origin, and here's my cursor. Therefore, look, the blue parts are of the same area. They are in the opposite sides of the x-axis, and the brown parts, they are of the same area, but they are on the different sides of the x-axis. They cancel each other when you integrate negative a to a f of x dx, so we get a big 0. This is the summary. Theorem 8, f is a continuous function on the symmetric interval. So symmetric interval is important here, right? Negative a to a, negative 5 to 5, negative 1 million to 1 million, negative 25 to 25. Okay, if f is even, then integral is twice of the 0 to a f of x dx, and if f is odd, it is automatically 0. Okay. Next section is about areas between the curves. Let's talk a little bit here, and then I'm going to get to the other lectures. So we have a function. We have a function f on top, and we have function g. Next, we are going to be talking about the area between two curves. We have two curves now, the blue curve and the yellow curve in the picture, as you would see. Upper curve is y is equal to f of x, and the lower curve is y is equal to g of x. We are interested in the area, finding the area between the two curves. As you would see, the area between the two curves is not a regular shape. And as you would see, the area is going to start when x is equal to a, and it's going to go until x is equal to b, right? So the question is, how would you find such an area? Okay, the idea is the same. We are going to form our rectangles. We are going to divide a to b into n equal subintervals, and then we are going to start building our rectangles, and then we approximate those rectangles, take the limit of that, and we are going to get what we want. Okay, so let's see. This is just explaining what we did before. You can just choose arbitrary ck in the interval and then get the area of one piece, one rectangle. Okay, so here's the definition. If f and g are two continuous functions where f is bigger than g for all x in the interval closed and bounded interval a to b, then the area of the region between the curves y is equal to f of x and y is equal to g of x from a to b is the integral of f minus g from a to b. That's all to it. So you're just taking the difference of the integrals. Okay, so let's see an example. This example contains, is made up of two functions, y is equal to 2 minus x squared, which is bigger than g function, which is g is y is equal to negative x function, right? Okay, and the interval is negative 1 to 2. And what you're going to do is you're going to say integral from negative 1 to 2 minus x squared minus x. Okay, that's what you would compute. Okay, so we are going to give some examples, areas between curves. As you will see in this picture, these are of course my old lecture notes, so the section numbers are different. We are still in 5.6 in Thomas calculus. Here, as you will see, we have the top function and the bottom function. We are interested in finding the area in between on the interval a to b, and you can find it if you read this fact: a to b f minus g dx is going to be equal to the shaded area of the region S, because we call it S. Now here are some examples for you. Example 1: find the area of the region S bounded above by y is equal to x squared plus 1, bounded below by y is equal to x, and bounded on the sides by x is equal to 0 and x is equal to 1. You would see, this region S is squeezed between these curves, and what's the top curve and what's the bottom curve and what's the interval? The interval is 0 to 1, and top function is top curve is y is equal to x squared plus 1. Bottom curve is y is equal to x. We have to take the difference x squared plus 1 minus x dx, 0 to 1. This is the area. We just apply the power rule and find the result, and the result is 5/6. So I'm not going to go into details how to do the power rule. Okay, we continue with the next example. Find the area of the region enclosed by the parabolas y is equal to x squared and y is equal to 2x minus x squared. And we want to draw the picture so that we understand which one is bigger. Here, this is a parabola. The second one is a parabola. Both of them are a parabola. First one you know how to draw. The second one, you can do this by completing to a square. So y is equal to, you factor out negative, you get x squared minus 2x, and then you are going to add plus and minus 1 to complete it to a square, and x squared minus 2x plus 1 can be completed as x minus 1 squared minus 1, and y is equal to minus x minus 1 squared plus 1. The vertex is going to be 1 to 1. Remember, y is equal to a x minus h squared plus k with the vertex vhk. So x minus h is the x component of the vertex, and k is the y component of the vertex, and a shows whether the parabola is looking up or down. Okay, now this is another example. This is the same example. So we draw the graph. This is y is equal to x squared, and we draw the other parabola looking downwards because a is negative, right? And then they intersect at 1. The intersection point, you know how to find the intersection point. You equate them to each other, and you get the common solution. And the interval is 0 to 1, so we write 0 to 1. The top function is 2x minus x squared, as I wrote here, top function, top curve. And the bottom curve is y is equal to x squared according to the graph. So 2x minus x squared dx. Let's say you weren't able to, you didn't have time to draw the graph, and now you just pick one of them as the top one and the other one the bottom one. if you get a negative answer as the area, then that would mean that you chose the top curve as the wrong one. Okay, so you can still do it like that if you're not sure which one is the top one. Okay, sometimes since we are not sure, okay, there's a fact. This fact is a new thing. So the area between the curves y is equal to f and y is equal to g on the interval a to b is a is equal to a to b absolute value of f of x minus g of x dx. Why do we do that? Because we don't know when, for example, the graph could be like this, interchanging, like which one is on top and the other one is bottom. So then because of that, we just put the absolute value. The absolute value is going to guarantee us which the top one minus the bottom one, regardless of we know which one is bigger on that interval. Okay. All right. So to make it clear, absolute value of f minus g is equal to f minus g if f is greater or equal to g, g minus f if g is bigger than f, then bigger than or equal to, doesn't matter. So this is what it means. Now this example is an example that find the area of the region S bounded by the curves y is equal to sine x and cosine x and on the interval 0 to pi over 2. Okay, what you could do is you can draw the graph of that if you know which one is bigger, or you can choose some points. For example, you can you would know that at pi over 4 this is going to be 0, so you're going to go actually this should be 0 to pi over 4. There's a typo here. Yes, this should be 0 to pi over 4 and pi over 4 to pi over 2. There's a typo here. Because 0 to pi over 4 its cosine is bigger, pi over 4 to pi over 2 its sine is bigger. You can either draw the graph or you can guess, etc. Okay, and now we are going to start writing our integral in two pieces. 0 to pi over 4 cosine x minus sine x dx is plus pi over 4 pi over 2 sine x minus cosine x dx. And you guys know very well the antiderivatives of cosine and sine. Antiderivative of cosine is negative sine, and antiderivative of sine is cosine. Okay. All right. So I think there's a typo here. Oh no, this is this. The antiderivative of cosine is sine. Sorry. The antiderivative of sine is negative cosine, I meant. Okay, now it makes sense. Then you just put them in and take these integrals separately and find the result is 4 over square root of 2 minus 2. Okay, and next topic is what happens instead of y is equal to f of x if the curves are x is equal to f of y. Okay,